Hello and welcome back to Mech Zone. Today we shall be starting with a new chapter, and this is the last chapter of our industrial engineering subject, and that is linear programming. That is linear programming. Now linear programming is used for the optimization on it is specifically used for the optimization of limited resources when there are number of alternate solutions possible for a problem. So if for a problem we are having ample amount of solutions, then which solution should be selected so as to optimize the limited resources? So it is a mathematical technique, and the term like linear, it is actually used for the variable, and it simply means that the relationship between the variable can be represented in the form of a straight line. So the relation can be represented in the form of a straight line, that is y is equals to mx plus c, where c is the y-intercept, y is the ordinate, x is the abscissa, and m is called as the slope of the line. Okay? It cannot be a square or a cubic relation. It cannot be a square or a cubic relation. It cannot be a square or a cubic relation. Now, what are the requirements for the linear programming? The first requirement is to have an objective function. The first requirement is to have an objective function. This objective function either needs to be maximized or needs to be minimized. If it is the cost, then we will go for the minimization, and if it is the profit, then it is to be maximized. So ultimately we have to optimize this objective function, and it should be clearly identifiable and measurable in quantitative terms like maximization of profit, sales, or minimization of the cost. The second point that we require is the constraint. The constraint or conditions, they will be given. Constraint or the conditions. So these are actually the limitations which are available. These are the limitations which are available to us. Now, what are these? These are actually the limited resources within which we are need to carry out the optimization task for our objective function. And first compulsory condition is to optimize the objective function, that all the constraints should be satisfied. So along with the satisfaction of these constraints, the satisfaction of the objective function is ultra necessary. So all the variables in the objective functions and the constraint should be linear, and they should be non-negative. All variables in 1 and 2, that is in the objective function and in the constraint conditions, should be linear and non-negative. It should be a non-negative quantity. So this is very important point. Now we come to what are the various assumptions of linear programming. Now we will discuss about the assumptions. The first assumption is of certainty. The first assumption is of certainty. In the linear programming model, the various parameters like objective function coefficient. Objective function coefficient means, for example, if we write 3x plus 2y, so 3 and 2 become the objective function coefficients. Constraint and resources are known exactly, and their values do not change with time. So they are not transient phenomena. They are not changing with time. They are actually remaining constant. Second is the proportionality. Second is the proportionality. Now in the proportionality, for the linear programming model, the quantities are based on the law of proportionality in the objective function, and the constraint के लिए क्या मतलब होगा? For the constraint, it means that if a product gives a profit of rupees 40, by selling 8 units, then the profit would be simply 320 rupees. If we have 8 units and we have a profit of rupees 40 for 1 unit, then the profit will be 320. 8 into 40, that is 320 rupees. So this is actually a proportionality relation. The third assumption is the additivity. The third assumption is the additivity, and in the additivity, the linear programming model law is the addition. Here addition is valid for resources and utilization. We can add the resources. It means if a product X requires 4 hours of processing on a machine, and machine A, sorry, this is for the machine A, and 5 hours of machining on the machine B, then the total time required for the complete product would be 5 plus 4, that is 9 hours. So this is the law of additivity. The fourth assumption is for continuity and divisibility. It is for continuity and divisibility. Now in the linear programming model, the decision variable are continuous, that is they are permitted to take any non-negative value that I have already told you earlier, and they will satisfy all the constraints. Okay, so these were all the assumptions that we have taken. Now we will start with the general statement of linear programming. We will start with the general statement of the linear programming. For example, we will be given maximize, or we can also be given minimize. Maximize Z or minimize Z is equals to C1 x1 plus C2 x2 plus so on up till Cn xn. So the first thing that we have to mark here is this is actually our objective function. This is actually our objective function that needs to be either maximized or it either needs to be minimized. Now the constraints or the conditions will be given as a11 x1 plus a12 x2 plus so on a1n xn less than or equal to b1, and so on. Here they will be called as the constraint or conditions. They will be called as constraint or conditions, and the conditions, that is x1, x2, x3 up till so on, they are always greater than or equals to 0. They are never negative. They are always non-negative conditions, where a1, b1 and c are the constants. Okay, aij, bij, cij, these are actually the constants, and xj is called as the variable. This is the variable where I can take the values 1, 2, 3 and so on, and j can also take the values of 1, 2, 3 and so on. Now what we have to do is we have to find out that value of x so that all the constraints are satisfied and our objective function is also optimized. So the main aim is to find out such value of x for which the function, that is the objective function, is maximized or minimized, that is it has to be optimized, and all these constraints or the conditions are also simultaneously satisfied. So to define aij, it actually called as the technological, it is called as the technological coefficient or substitution, and bi is called as the resource value. Bi is called as the resource value. Cj, or it is called as the profit coefficient, and xj, it is actually called as the decision or choice variable. It is called as the decision or choice variable. Now we can solve linear programming either by graphical method or we can also solve it by simplex method. Out of the two, the graphical method is the easiest and it is mostly preferred. However, very limited amount of questions have been asked from the simplex method. I will not discuss any problem on the simplex method. Rather, I would discuss what are the main features and how can you guess the answers. Whereas I will be discussing about the graphical approach, that is the graphical method, which is the most widely used method. Now we will start with the graphical method for linear programming model solution. So what are the general steps that we have to follow? So the steps are as, first step is we have to identify the problem and define the decision variable, objective function and the constraint. The second one is we have to draw the graph that includes all the constraint and identify the common feasible region. So we are mainly obtaining the common feasible region. For the third case, or the third point is we have to find out the point within the feasible region that optimizes the objective function. So we have to optimize the objective function. How we can optimize? By selecting those points which are actually lying in this common feasible region. We are going to use only those points. Now the fourth and the last step is, after finding out that point, the point that will be find out, it will give the final solution. It will give us the final solution. Now we will discuss about what is feasible region or solution space. Feasible region or solution space. Feasible region or the solution space, it is the region where all the constraints are plotted on a graph and we get a common region where all the constraints are simultaneously satisfied. So this region is known as the feasible region or the solution space. Any point within this region can be our solution under the given constraint. This feasible region must be a convex set, otherwise linear programming cannot be applied. Now for the convex set, it simply means like this, and for the non-convex set, it simply means like this. That means it should cover all the points within the given space. So LP can't be applied for this region, whereas LP can be applied for this type of region. What is a convex set? Now I have introduced a term, that is convex set. What actually we mean by convex set? If any 2 points are selected in a region and the line segment joining those 2 points lies completely within the region, then it is said to be a convex, otherwise it is said to be a non-convex. So this is a non-convex type and this is a convex type. So for this particular region or for this particular case, we are going to apply the linear programming, whereas for this we are not going to apply the linear programming. So now we will discuss a linear programming problem which will be solved by graphical method. So this is a type of problem which can be given. This is the objective function in which we have to maximize. That means it must have been the profit function. Now subjected to these are the constraints which have been given, and x1, x2 are actually non-negative. This is a very but obvious statement that we can find from here. Now this is actually the format. What the problem has been asked is we have to maximize 12x1 plus 16x2, which are subjected to these two conditions. 10x1 plus 20x2 is less than or equal to 120. 8x1 plus 8x2 is less than or equal to 80, such that x1 and x2 are both greater than or equal to 0. That means they are actually non-negative. They are actually non-negative. Now we know that the inequalities cannot be solved, so we will convert inequations into equations by simply removing the lesser than or greater than sign, and this becomes equal to. Okay, so the first equation becomes 10x1 plus 20x2 is equals to 120. Now what we will do is, first we will substitute x1 is equal to 0 and find out the value of x2, and then we will substitute x2 is equal to 0 and find out the value of x1. So when we keep x1 is equal to 0, x2 becomes 6, and we will keep x1 is equal to 12, x2 becomes 0. So we are actually obtaining 2 points 0, 6 and 12, 0. x1 is actually corresponding to the x-axis and x2 is actually corresponding to the y-axis. Now we will plot these 2 points here, like 0, 6 and 12, 0. Now we will join those 2 points by means of a line, and that line is actually representing the first constraint that was given. Now we move for the second line, that is 8x1 plus 8x2 is equals to 80. Same procedure will be applied here also. First keep x1 is equal to 0 and corresponding value of x2 becomes 10. Next is keep x2 is equals to 0 and the corresponding value of x1 becomes 10. Now again we obtain 2 points, that is 0, 10 and 10, 0. On that graph we will make those 2 points. And what we will observe that for this constraint and this constraint, this red hatched portion is actually getting common to both these lines or both these constraints. So this common region which is obtained by the after drawing these 2 constraints will be the feasible region. Now what we will do next, we will identify the shape of the feasible region, that is A, this point I am naming at B, this is C and this is D. So we have to determine the coordinates of A, B, C and D. The coordinates of A are 0, 0 because this is the origin. B is 0, 6. D has also been given in 10, 0. Whereas the coordinates of C can be simply evaluated by simultaneously solving the 2 constraints, and the coordinates of C will be obtained as 8, 2. Or if you are drawing it on a graph paper by taking the suitable scale, then you can directly see it from the graph itself. Now C coordinate has been already obtained. Now this is corresponding to x1, this is for x2. We have obtained 4 sets of value for x1 and x2. What we will do is, we will keep those 4 sets of value one by one in our objective function, and the objective function which was given as this was 12x1 plus 16x2. So for putting this value in our objective function, we will obtain as 0. If we put that x1 and x2 corresponding to b in the objective function, we will obtain 120. And if we put c point, if we put in the objective function, we will obtain as 128. And if we put the d point in the objective function, we would obtain as 96. Now out of those 4 values, 128 is the largest value. And since we were to optimize such that we need to have the maximum, therefore this value is chosen as the answer. And if it was asked for minimization, then 0 would have been the answer. So this value is obtained corresponding to x1 equals to 8 and x2 equals to 2. So at 8, 2 we are having the maximization, that is the maximization occurs at this point. Maximization occur at this points. Now what we will talk about, we will talk about binding and non-binding constraints. For x1 is equals to 0 and x2 is equals to 6. So what we are doing is, if we put these values in the objective function, we obtain 120 is less than or equal to 120. So this becomes a binding constraint. Whereas the constraint which does not give the exact value as that of this value becomes the non-binding constraint. So this is how we are going to find out the feasible region, and then we will decide the feasible solution for our given problem. Now we will discuss something important, and this is really very important about our solution. Now we will discuss about the special cases in case of the linear programming problem. So, special cases. For the special cases, the first one is infinite number of solutions. If what will happen, or what are the conditions to obtain infinite number of solutions? Now we have to remember that for the infinite number of solutions, the slope of objective function, the slope of the objective function, it is actually equal to the slope of binding constraint. The slope of the binding constraint. If this is happening, then we will have the infinite number of solutions. So this is actually used for the minimization problem. Okay, and generally the maximum value of the objective function, we have to remember one thing, that the maximum value of objective function is obtained at the corner points of the polygon. The polygon that we have obtained here is A, B, C, D. So we will obtain the maximum value generally at the corner points. At the corner points. Okay. An infinite solution, infinite number of solutions simply means we get the same optimum value of the objective function for the different varying variables. If we are having the different varying variables, we will obtain the same value corresponding to those variables. So this was about the infinite number of solutions. The next special case that we will discuss here is the no solution case. The no solution case or infeasibility. No solution or infeasibility. Now, in case of no solution or infeasibility, there will be no common point. For example, one constraint is like this. Now, if it is less than or equal to, we will indicate the arrows towards the lesser sign. And for this constraint also, we were having the less than or equal to. So I have written, or I have made the arrow in the downward direction. However, if it would have been given greater than or equals to, then this arrow would have been pointing upward. Okay, so here for example, if we are having in this direction greater than or equal to, and the second constraint is like this, so we are not having any common portion. So there is no common point for this type of graph, and hence in some conditions what will happen, constraint may be inconsistent in such a manner that it is not possible to find a feasible solution where all the constraints are satisfied. So this would actually represent the no solution case. Here we would obtain no solution. Next we come to the third special case, that is the unbounded solution. Next we come to the unbounded solution. For example, if the graph is like this, and this is also greater than or equals to, so actually this entire portion becomes our feasible region. Now since this in some conditions we see that the highest value of the objective function moves up to infinity, and it simply means that the common feasible region is not bounded by the limit on the constraint. Therefore this type is termed as unbounded solution. This type of solution is called as unbounded solution. So with this we come to the end of this lecture. We hope कि आपको हमारे लेक्चर्स पसंद आ रहे होंगे. आप हमारे चैनल पे या हमारे फेसबुक के पेज पर हमें अपना फीडबैक दे सकते हैं, हमारे साथ अपनी प्रॉब्लम शेयर कर सकते हैं। आप हमारे चैनल से हमारे वीडियोस के डिस्क्रिप्शन में हमारा सारा स्टडी मटेरियल फ्री ऑफ कॉस्ट दिया हुआ है, यू कैन डाउनलोड इट फ्रॉम देयर। और अपने फ्रेंड्स को और अपने कलीग्स को भी हमारे चैनल के बारे में बताइए, सो दैट दे आर ऑल्सो बेनिफिटेड, बिकॉज एवरीथिंग इज अवेलेबल एब्सोल्युटली फ्री ऑफ कॉस्ट ऑन आवर चैनल। ऑल द क्वालिटी वीडियो लेक्चर्स फॉर ऑल मैकेनिकल सब्जेक्ट्स, हमने कोई भी सब्जेक्ट कोई भी टॉपिक नहीं छोड़ा है। अगर कोई भी छूट जाता है देन हमारे व्यूअर्स बता देते हैं, देन वी कवर इट दैट ऑल्सो। सो आप हमारे चैनल के बारे में सबको बताइए ताकि उन्हें भी बेनिफिट मिल सके, एंड हमारे वीडियोस को बार बार देखिए ताकि आपके डाउट्स जो हों वो क्लियर होते जाएं और आप प्रॉब्लम्स भी लगाते रहिए। सो विद दिस वी कम टू द एंड ऑफ दिस lecture. In the next lecture we shall be discussing something on simplex method, and that would be the last lecture.